Okay, let's just start. Hopefully the video quality is a bit better this time. I've got a different webcam for it. And yeah, I'll have to restrict to writing on this section of board so then the recording doesn't miss out on anything. Okay, so we're going to start with two of the last questions from tutorial 2 that we didn't get to last time. So first is question 6. Is that not too high? So question 6 is that you have a paramagnetic substance undergoes a whole bunch of process. Magnetic field is applied to it under adiabatic conditions. Heat is removed, so it causes magnetic refrigeration. It's like a pretty well-known thing in condensed matter physics. And you want to find here just an expression for the rate of change of the adiabatic temperature increase. So if you have the question in front of you, is process 1 or 3. So here you have some H, which is your auxiliary field. Or like, I think what Paul calls it is the applied field. And yeah, this is kind of like constant. And you also want to change T. So you want to change the temperature. So you want to find an expression for the rate of change of the temperature with the field. So yeah, for this, you take first you take the equation of state you have. So you know the magnetization, which is a function of the H field, and the temperature is given by the Curie constant. Okay, for some reason I call it A here instead of C, but it's the same thing. Times the applied field divided by the temperature. And here you are given a Maxwell's relation. So the change in entropy with respect to the applied field at constant temperature is equal to change in magnetization given by change in temperature at constant field. And here you want to find is the change in temperature with respect to H at constant S. So I guess I shouldn't have wrote this down. I don't know why I did that. Okay, so to find this, you use the you start with the cyclical rule. So if you have any kind of like these partial differentials with 3 variables, and you can always just kind of pretend that x, y, and z, and then write out the whole cyclical rule for these 3 variables. So let's just add in the other 2. So you have dt dh at constant s. So then the other one will be dh ds at constant t, and the last one will be ds dt at constant h, and this whole thing is equal to -1. So in this case, we want to find this. So to do that, we need to evaluate these 2 terms. Once you can evaluate these 2, then you can just take to the other side, and you've got an expression for dt dh, which is what we want. So in this case, let's start with the first term here. So dh ds at constant temperature. So dh ds at constant temperature, you can write this with the, I'm not too high, okay. Write this with the inverse rule. So the reciprocal rule, ds dh at constant t to -1. And ds dh at constant t, you can use the Maxwell's equation we given before in the question to write as dm dt at constant h, but it would just be inversed because we had to reciprocal the whole thing. So this is actually the same as dm dt inversed at constant h. So you technically can leave this for now because you do have an equation of state for m. So you can take this derivative at constant h and plug this derivative of this into the expression. So we can just leave this alone for now. So let's look at the other term, which is ds dt at constant h. So for this one, you have to think about, okay, the, what's it called? Sorry, the change in heat, the heat exchange is equal to TdS. So, and the change in heat dq is also equal to the heat capacity at constant field, in this case, times by the change in temperature. So both of these hold. So then if I want to find ds dt in this case, if you think about dividing these two through, so ds dt will equal to the left-hand side will equal to 1, and then you have t divided by c at constant h. So rewriting that, you get ds dt is ch divided by t. So just manipulating these two, combining these two equations together. And then if you think about this, is already a constant h, and this is a differential derivative. So at constant h, partial derivative and total derivative doesn't really make a difference. So these two are equivalent in that sense. So ds dt at constant h is given to you by c little h divided by t. So now we got both of them, so we can just put these back in. So we get dt dh at constant entropy is given to you by minus the inverse of dh ds t, which is the first term, so then it will be minus dm dt at constant h inverse, and then times by ch divided by, t divided by ch, because you gotta take this other side, so this is technically flipped. So it's the inverse of that, so it's t divided by ch. And then now all that's left to do is just evaluate this. So you take that and you differentiate it, and you should hopefully get, as a, so this whole thing should be n divided by ch. Yep. Okay, so now that we have this differential equation, I'm gonna rub something out so I have more room. Okay, we don't need this anymore. Sorry? Yeah, because we had dHds and then we're to invert. Oh, right, sorry. So you think this is regular dm dt? Yeah, sorry, yep. Yeah, because this inverse and that. Sorry, let me think. So on left hand side, you had ds dt, or dh ds. In taking the right hand side, you get ds dh, and it's dm dt. Yeah, sorry, no, there's no inverse here. Cool. Okay, so anyway, so now we just want to solve this differential equation. So we just integrate over h. So you get the change in temperature going from some temperature to another temperature adiabatically is given to you by the integral from the initial field to the final field of m divided by ch dh. And this is a well-known expression for magnetic refrigeration. And that's the answer for this. Okay, well, good. Cool. Okay, so then we'll go to question 7. So question 7 is a whack. I think Paul must came up with this himself. So you have a container of two, I don't know how to pronounce this, immiscible liquid. I think what it means is that they don't exactly blend together like oil and water, that kind of stuff. And they undergo the following process, assuming all dissipated work goes into breaking up clumps and that VA is larger than VB. So you got more of the liquid A than liquid B. So for the first part, you want to know what is the work done by two identical spheres of liquid B coalescing at constant temperature. So you're starting with two liquid B kind of little droplets, and then they combine together into one big droplet. So in that case, your final volume is exactly equal to 2 times the initial volume. So assuming you didn't lose anything anywhere, you're going to get the two of them just perfectly combining together to form a larger sphere. So to think about this, you have to think about the work done, you have to go slightly back. So you think about the surface tension. The surface tension of a liquid is given by, so sigma is equal to half F divided by L. What this essentially means is that if you imagine having 3 immovable walls, so like barriers, and then you put a liquid in here, and this liquid forms like one edge layer here. And this volume could expand in this direction, so this is the delta X direction, it could expand that, it could fall that way or this way. Then this side length L is the L here. So the longer this edge is, the smaller surface tension you have. Whereas if you have a rather narrow edge and just like one small concentrated droplet, you'll have a larger surface tension. So this is what sigma is there for. And the half is representing that if you think about the surface where this edge that you're considering, you technically have 2 faces, one facing outside, one facing inside, and they both provide tension force. So this half just represents this is the tension force only on a single side. Okay, so since this is the surface tension, now if we just multiply both the top and bottom by delta X, so multiply top and bottom by how far it could move in this lateral direction that is allowed to move in, then the numerator is FR. So this numerator is just going to be the work. So equal to half times the work divided by denominator L delta X. And L delta X, if you look at this change, it's just going to be the change in area. So this area and how far it has moved is covered by delta X times by this entire length of the surface. So sigma is approximately given to you by the work divided by the changing area. So you can reverse this equation to tell you that the work done by water droplets or combining water droplets related to surface tension is given to you by sigma times by delta A. So that's the work expression we'll be using. So if that's the work done, then we need to find out how much the area has changed. So if you think about 2 spheres, the first expression to consider is the volume of the sphere squared. So volume of sphere squared is just 16 divided by 9 pi squared r to the 6. And the other one is the area cubed of a sphere. So area cubed is 64 pi cubed r to the 6. So now you have both of them depending on radius to the power 6. So you can combine these two and write an expression to express volume in terms of area. So you get V squared is given to you by 16 divided by 9. Oh, sorry, not 16. V squared is 36 pi V squared is equal to area cubed. So then now you can write area as a function of volume is equal to 6 root pi times the volume to the power of 2/3. So then given this formula for the area in terms of volume, if we went from the initial volume to a final volume that's double our initial, and we can see that the final area is equal to 2 to the power 2/3 of the initial area. Because if you just put in 2 times V in here and then take the 2 out the front, it will carry this power 2/3. And the rest of the terms in the bracket will just equal to the initial area. So your final area is related to the initial area like that. So now we can just work out the work to say the work done by this coalescing is given to you by integral from the initial area to the final area of this surface tension sigma times by the change in area. And the surface tension sigma is given to you in the question. The expression is, let's see here, sigma is alpha 1 minus T divided by Tc to the power of n. So alpha is some empirical constant that you have to go measure. So is n. Tc is a critical temperature. So the surface tension is technically temperature dependent. So if the temperature is larger than Tc, temperature is less than Tc, then the surface tension behaves fine. But then at Tc, the surface tension vanishes. So if you heat up a liquid at one point, it's not going to be able to hold its shape. But in this case, we'll just consider T is less than Tc. So putting this expression into here, it doesn't actually care about the area at all. So we can just take the entire thing out the front. So the work is just given to you by alpha 1 minus T divided by Tc to the power of n times by the change AF minus AI. I think I missed something here. Oh, sorry, this is actually over A as well. Then the question, sorry. Yeah, sorry. My bad. Is sigma A is given to you by that. So then you do get one factor of A in there. So you get 1 over A dA integrated from the initial area to the final area. So then that will be 2/3 times log of 2. Because you have a log and then initial area divided by final area divided by initial area, you just get a 2 to the power 2/3 in there, and take the index out the front and leaves you with just log 2. So if T is less than Tc, you can see this work is positive. So that kind of answers our question from part 2, is asking, is this process spontaneous? So this is the work done by the water molecules coalescing. So if the work is positive and they're doing work, that means they're losing energy. So the final state is less energetic than the initial state. And if you have a lower energy state, then the system will want to go into the low energy state if it can. So the condition is that if this energy difference, so the work done, is larger than the entropy difference to break down the water droplet into smaller droplets, then this will be spontaneous. So yes, it is spontaneous. Mainly due to energy consideration, that it's energetically favorable to combine into a lower energy, bigger bubble. And that kind of physically makes sense, because if you're a bigger bubble, then you have less surface tension, so you don't have to hold on as hard. And if physics is lazy, then it wants to go there. Okay. Yeah.
I'm sorry, I think you, so if the work, so you mean if the work done is positive, then, but what about the heat change?
Yes, so that's why we said there's a slight caveat. It's like you have to consider that if the energetic difference has to be larger than the entropy of going back. So you'll have some entropy. If you have some entropy of breaking, if you break down one big one into two smaller ones, if this entropy change is large enough, so like enough heat is involved, then you wouldn't want to, because you will naturally want to go to a maximizing state for the entropy. But if the energy difference is larger than this, so the heat lost is not worth the amount of energy that you gain by going to the larger state, then you would spontaneously combine. Yeah, so you have to compare it to the entropy to know. Yeah, okay. Okay, part 3. Part 3 question is, what is the increasing temperature during the adiabatic coalescence? So in this case, we want to know if two things combine adiabatically, how does the temperature change? So in this case, we again think about what is it that we want to find? We want to find the change in temperature with a change in area at constant S. Because two things coalescing, you can just imagine the surface area is increasing. And so that's the temperature change with respect to area. And it's happening adiabatically, so S. And again, we look at these three variables and we try to construct a cyclic rule with these three variables. So the other two terms are going to be dA, ds at constant T times by ds, dt at constant A. And that's equal to -1. Okay, so pretty much the same as the question 6. We know we want to find this. So then we need to evaluate these two first. So let's start with the first one. So dA ds, we know we're going to take to the right-hand side. So let's just consider what happens when it's inverted. dA ds at constant t to the -1. So this, you can use a Maxwell's equation to relate to the sigma dt at constant a. You might be wondering where did I pull this from. If you think about the normal Maxwell's equations, Maxwell's relations, you do have one that says ds dv. Ds dv at constant t is equal to dp dt at constant v. So this is your standard Maxwell's relation that you would know, derived from the first law of thermodynamics. But remember, our work is now given to us by sigma dA rather than p dv. So that you can think about this as exchanging all times that you see the pressure with the surface tension. And every time you see a volume, you replace it with area. Since these two are both equivalent definitions of work, and in this particular context, we want to use this definition. So every time I see P, I swap it with sigma, and every time I see V, I swap it with A. And that's basically how we get this. This is inverted, so it looks upside down. But so that's the -1. So yeah, so that's how you get that Maxwell's equation relation. Keep saying equation. Okay, and the last one's ds dt at constant a. So ds dt at constant a, so -1 because we want to take the other side. This one, you have to think about it again with the expression for heat. So dq is equal to t ds. And so ds dt, so you can think about this as a chain rule that dq ds is equal to t. So you can try to chain rule this by getting, rather ds dt, you get 1 over t dq dt at constant a. Sorry, it's all smudgy. There's a t here. So we just use a chain rule of this dq dt is a dq ds is t to swap out this ds for dq, and then getting a 1 over t factor out the front. And then also now, if you look at this term, dq dt at constant a is by definition the heat capacity at constant area. So it's how the heat exchange happens to affect the change in temperature. So that's just C sub A. Yeah, so this whole thing is actually equal to CA divided by T. Okay, so now we can invert this equation and say dt dA at constant entropy is equal to dq minus dq, not dq, that's a sigma. The sigma dt at constant A times by CA divided by T. Why is this upside down? Yeah, okay, that's fine. Yeah, and now you have the expression for sigma. So sigma is still alpha on A, 1 minus T on TC to the power of N. So you can evaluate the sigma dt at constant A, which is easy because that means this is a constant, this is a constant, this is a constant, and this is a constant. So it'll just be a polynomial derivative. And then you can sub this back into there. And that's your expression for the change in temperature with change in area. Yeah, and for part 4, when I ask, is this reversible? So it still hasn't changed the fact that when you're considering the work done, it's the same as part 1. So when you have 2 smaller droplets combined to a large droplet, it's energetically more favorable to be in the large droplet state. But then in this case, because entropy is set to be 0, and we said before, we have to compare the energy difference to the entropy. So now we have no entropy, so energy is definitely the more important factor. And so this system will also spontaneously combine. So yes, also spontaneous. And I'm not able to top 5 as well. To be fair, he did say it's more food for thought. I just thought about it for a while and I couldn't really come up with anything meaningful, to be honest. Okay, so then let's move on to tutorial 3. So try to do the first half today because I think the second half touches on material that's not quite there yet. Okay, I think question 1 is too easy. Like you can take that as like an easy exercise at home. I won't take that away from you. So let's start with question 2. So this is shoot 3. Question 2. Question 2 is derive an expression for the entropy of a rubber band or polymer of length L and tension tau. What can you infer about the force behind the elasticity of the rubber band? The experimental equations are given by, so the tension tau is C alpha T L minus some equilibrium length L naught divided by L naught. And your internal energy is given by C L naught times by the temperature T. So again, in this case, the work is a bit like non-standard. So if you think about pressure, like fundamentally pressure is the force per unit area. So it's like F divided by A, approximately. And volume is, you can think about it as an area times by some length. So usual expression of work as P dV will be given by, can also be thought of as given by these two separately. But in this case, for the rubber band, we'll instead have the tension times by L. So we cancel out these two A's and then just have the tension force and then times by the remaining L that's left. Rather than a pressure times by a volume, we combine these two areas from these two separate terms and left with just a force term, that's tau, and a length term. So if that's our work, then we can write down the equation for the entropy. So ds is equal to 1 on T du minus tau divided by temperature dL. Okay, and now we can sub in all of the things that we got from here. So for 1 on T, we can use this to get C L naught divided by the internal energy U du. And for the second one, we use both the tau and the U, so we get minus C alpha on L naught, L minus L naught dL. So the temperature cancels with that. Okay, and now you can just, this is just the easy integral, both of them. So you can just evaluate integral. So you get the entropy as a function of U and L is given to you by C L naught log of the internal energy U minus C alpha 2 L naught L minus L naught squared. Okay, and the observation you want to make about the force is that entropy increases as L decreases. Assuming L is always going to be larger than L naught, because you can't really get a rubber band to be shorter than its equilibrium length. But yeah, if you stretch a rubber band out, then the entropy will want to increase by decreasing the length of the rubber band. So the elasticity, elasticity force is technically trying to maximize entropy, which is the equilibrium state. So that makes sense, as we observe that every time you pull a rubber band longer than its equilibrium length, it's going to decrease that length to come back to the equilibrium. All good? Okay. Is that a question? No. Okay, then question 3. So this one is, again, the hint says it's unsure about the solvability of this question. But, and I did get a different answer to the tutor last year, so I don't really know what's going on. But I think every step that I took, I could justify somehow, so it's not that whack. But at the end of the day, okay, you want to derive the expression for entropy of an ideal paramagnet using the equation of state given previously. I guess previously means in your lectures. Also draw a H, M, and TS diagram for a magnetic Carnot cycle. So just reminder, Carnot cycle is 2 adiabats plus 2 isotherms. Okay, and yeah, like if you watch the lectures on the magnetic stuff, you realize that there's like a million different ways you can define your work and energy and all that. So I picked a particular definition where it works for me. They're all equivalent, like Paul said, it's just like up to like 1 Legendre transformation. So the way I picked it is, okay, the change in entropy is always going to be 1 on T du plus 1 on T dW. So the question is, how do we pick this work? So in this case, I take the U star definition. So I use 1 on T du minus VB on T dm. So I think this corresponds to my internal energy is the U star representation. Okay, and in that case, since I picked that internal energy, then my internal energy little u, so the specific internal energy, is technically, using that definition, would be mu naught times m times the auxiliary field h. Okay, so first I want to rewrite the entropy equation in terms of specific quantities. So d little s is given to you by 1 on T d little u minus B on T dm. So I got rid of this volume term. And yeah, now all you have to do is take this, the internal energy definition, plus the equation of state, so the Curie's law still applies, so M equals CH on T. So just subbing in these two into this equation here to try to get it, to simplify it down, then you will get ds, the little s will equal to mu naught m squared. Sorry, skip the step. Let's take it easy. You first get m divided by ch. So that's just subbing in 1 on T from the magnetization, the Curie's law of magnetization, d little u, and then minus mb on ch dm. So that's also subbing out 1 on T for that. Okay, and now I want to use the internal energy definition. So take this out here. So we get d little s is equal to mu naught m squared on c du on u minus mb ch dm. So I just subbed out the h with the internal energy formula to get it in terms of just the magnetization field and the internal energy little u. At this point, I then take the weak field limit. So I'm assuming that in this case that whatever material that we're considering, it might induce an internal magnetization, but it wouldn't be that big. So m is actually a relatively small number. So you have a pretty weak induced magnetization. So if in this limit, then I can assume that I could throw out any nonlinear terms in m. So m squared, if m is a small number, then m squared is going to be like a negligible number. So I could throw out any term that's proportional to m squared. And if m is very small, then I could also assume that my physical field B is related to the auxiliary field by h naught, not h naught, mu naught. So taking these two approximations, I then simplify this by completely deleting the first term because it's related to m squared, so it's going to be very negligible. And then I can also simplify the second term because I have a B divided by H, and with the weak field limit on the B field, then these two can cancel out and leave me just with permeability mu naught. So therefore, ds is approximately in the weak field limit equal to minus mu naught m on c dm. And if I now integrate this to get s is equal to s naught, some constant, minus mu naught on 2c m squared. And I can use this to sub back to get it in terms of the h. So I get s naught minus mu naught c on 2 h squared on t squared. And I think that doesn't look too weird to me, because if you have a paramagnet, the more you decrease its temperature, this term gets larger, so you get a larger negative number. So you decrease the entropy at lower temperature, which kind of makes sense. And then at higher temperature, you increase entropy, and then you start destroying the magnetic moments inside. So it's not that whack, but I mean, there could be other ways of doing this as well, depending on how you define your work and stuff like that. So to draw this counter cycle, then that you could have done without doing any of this. So first, MH graph. This you can just take it straight from Curie's law. So in this case, you know, adiabatic processes, adiabats corresponds to M being constant. So in a Carnot cycle, we have two adiabats. So you have two flat lines. N's my y-axis. Sorry, we're too far up. N's y-axis. So you'll have like a flat line and a flat line. And then the two isotherms are constant T. So T equals constant. But then I'll have a TH and a TC because I'll have two different temperatures in there. One's high, one's low. And if you look at Curie's law, M equals CH on T. If I change T, then all I'm doing is changing the gradient with respect to, for the M versus H graph. So I'll get one straight line at some gradient and another straight line with a slightly different gradient. So it'll look like kind of a pushed over trapezium. And this could go whichever way. So these are the adiabats. And these are the isotherms. And for the TS diagram, it's incredibly boring. It's just it's also a rectangle. I mean, it's got nothing to do with this because by definition, adiabats and isotherms just look like flat, straight lines in a TS diagram. TS. So it looks still exactly like that. So nothing fancy there. Okay, everyone happy? Yeah. All right, question 4. So this one's using van der Waals gas to try to derive an entropy expression. So van der Waals gas gets a much more complicated equation of state. So you got P plus A n squared on B squared, V minus MB is equal to NKT. And your internal energy is also slightly more complicated. Okay, but solving is really simple. All you have to do is just write down the expression for entropy and then just subbing these in and then going through the algebra. So let's do it all in specific values. So I'll write lowercase little s. So d little s is 1 on t d little u plus p on t d little v. So these are specific values, and okay, call this equation 1 and this equation 2. So let's take equation 2 first to try to get the 1 on t coefficient. So from equation 2, if I write this in specific values as well, I get little u is equal to f on 2 kt. So dividing everything by n minus a divided by little v. And yeah, so now you can just turn this into a 1 on t expression. So 1 on t is equal to f on 2 kt, k, divided by u plus a divided by little v. All right, so that is ready to be subbed into here. So the other thing we need to work out is what is p divided by t. So that we use equation 1 to do. So from equation 1, we get, again, putting into specific values, so p plus a divided by little v squared times little v minus b is equal to kt. So then from that, rearrange this, you get the pressure P is equal to kt divided by v minus b minus a divided by v squared. And then just divide the right hand side by t to get p on t is equal to k on v minus b minus a on t v squared. And rather than having this t here, you can sub in the 1 on t expression that we got over here into here. So you get a on v squared times by that whole thing there. So f on 2k divided by u plus a on v. Okay, so now we've got a p on t and we got 1 on t expression here. All we should have to do is sub it into there. So you get d little s is equal to f on 2k divided by u plus a divided by v du plus this whole thing there, but we're going to separate into 2 terms. So the first term is just going to be k divided by v minus b dv. So that's k divided by v minus b dv. The second term, we're going to slightly rearrange it. So we're going to just, before we rearrange it, just write it down, minus a on v squared f on 2k divided by v, u plus a on v dV. But we're going to think about if we have the differential of V, A divided by V, and A is a constant, so we just differentiate V. So we actually get minus A on V squared dV. So I can substitute this A on V squared dV for just the differential of A divided by V, all inside the differential bracket instead. So we're going to do that here to simplify this second term. So you get this is equal to F on 2K divided by U plus A on V du plus F on 2K divided by U plus A on V d A on V. And then plus this last term that just stays the same. Okay, and now we see we have two of the exact same coefficients here. And we've got two differentials. We can just collect them. You can combine these two into F on 2K divided by U plus A on V du plus A on V. Since addition just distributes normally under differentiation, so you can combine them together without any problems. Plus K divided by V minus B dV. And this is now you're going to be, if you integrate this, you're integrating over this combined variable of U plus A on V. And in the coefficient, you got 1 over U plus A on V. So it's just going to be a simple log integral. And this is also going to be a simple log integral. So you can now evaluate this integral for S. Very straightforward. So then integrating, you just get S is equal to some initial value S naught plus F on 2K log of U plus A on V. And then plus K times log of V minus B. So that's the answer. So nothing too weird here, except recognizing that you can sub in this like A on V differential rather than just integrating over V. Okay, all good? Yeah.
I do have a question. When you say looking for the little u, you say we divided by capital N on both sides, but I'm thinking like, but for the correction side where it's n squared over b, you have n squared completely off. I just want to know this meaning or not.
Oh, because one of the, so yeah, you after divided by, so you got u equals F onto nkt minus a n squared on v, right?
Yeah.
So after dividing everything by n, you lose one n here, lose this n, and you get divided by n.
Yeah.
So then this n on v becomes a little v. Yeah, so that becomes a specific volume. Okay, perfect. We got just enough time for the last question 5, and then call it there. All right, question 5. You have 2 infinite reservoirs at temperature T hot and T cold. Heat is allowed to flow between them at a constant rate. Explain why this is. The explanation is not that hard. So you have 2 infinite reservoirs, and then they are in contact with each other by some diathermal wall. And this diathermal wall, assume it's like some delta X in thickness. And this is T hot, and this is T cold. And yeah, from high school, you will probably remember this formula. So the rate of the flow of the heat by contact is equal to some constant minus K times the cross-sectional area between them times the change in, the difference in the temperature between two reservoirs divided by the thickness of the wall. So in this case, we have two infinite reservoirs, which means that it doesn't matter how much heat I'm able to pump from one to the other, their temperature is not going to change because it's like infinitesimal difference to them. So that means TH and TC are both constant. If they're constant, then the difference in temperature between them is also constant. And if this is constant and everything else, like assuming your A and delta X, they don't change because your heat bath has been like set up and just left there, so it's not going to geometrically morph. Then if delta T is also constant, then R is forced to also be constant. So it's because the infinite nature of the reservoir that the temperatures don't change forces the heat exchange to stay the same. All right, so that explains why R is constant. But now we want to work out the entropy. So okay, the entropy is actually not that difficult to work out. So let's start with the cold bath. So for the cold bath, it's going to be the one that's receiving heat. So your change in entropy for cold bath is going to equal to a positive injection of dq divided by T. And the temperature is going to be at T cold because that's the bath that you're in. So in this case, you can think about the change in entropy with respect to time. And that's going to be equal to 1 over T cold change in heat over time. And this change in heat over time is exactly the rate of the heat flow, which before we defined it as R. So this is just going to be equal R over TC. And these are both constant. So then if you want to find S, SC will just change with some initial entropy plus R divided by TC times by time. Because both R and TC are assumed to be held constant in this case. And when you do this for the hot bath, is exactly the same thing, except you're now considering a negative dq because the hot bath is the one that's losing heat. So you have a minus dq divided by th. And similarly, the entropy hot dt is equal to 1 on th, sorry, minus 1 on th dq dt. And that's the same R, that's the same constant rate of flow. So that's minus R on th. And if you integrate it, you get something similar to that, except you get a minus sign. But if you now look at the change in the total entropy with time for this entire system, the change in total entropy will just be the sum of the entropy change in a cold bath plus the entropy change in the hot bath. So that's just equal to ds cold dt plus ds hot dt. And when you add these two together, you find that it's going to equal, I've got a little bit of space left. So it's going to be equal to R times 1 on TC minus 1 on TH. Sorry, I'm going to write that again. I'm running off the board here. ds total dt is equal to R times 1 on TC minus 1 on TH. And since TH is larger than TC by definition, then 1 over TC minus 1 over TH, this is a positive number. So your entropy is actually growing over time, even though these two heat baths are exchanging like a negligible amount of heat that nobody cares about. But remember that during the exchange of heat, if any energy is lost, then you will generate entropy. So in this case, you will still expect a non-zero increase in the entropy, even though you're not actually doing any physical change to the temperature. Okay, I think that's all today. Any questions? No? All good? And I'll see you guys next week. Hopefully this recording is better.